In the last subsection, we'll talk about asymptotics and big O notations, because that's the way how computer scientists usually express statements about the efficiency of algorithms. And it's a useful approximation and just a piece of vocabulary that you need to know if you talk about algorithms to people. But instead of just showing, let's see how people are on this. I'll decide a bit on your answers, how quick to go. I don't want to bore people with things they already know, but also I don't want to go too fast for anyone who's not seen this much before. I'd love to see 100 votes, but I don't promise I'll wait for it no matter how long it takes. I'm a naturally impatient person. All right, I think that's good enough for seeing the rough picture. So we have a majority who knows this, but there's a substantial bar below with the I don't know big O at all. So let's have a look at that. And also for all the others, we'll come back to this, so no real explanation on this. I want to motivate a little bit why people use asymptotics before we dive into this. I'm not sure if that's very prominent or very obvious to anyone. The key thing why we use asymptotics is because the analysis of algorithms focus on large inputs. And the reason for doing that is if you're just concerned about small inputs, maybe there's a way to just list all the small inputs you need, or you do extra special cases for certain specific small inputs. So by focusing on large inputs, you can abstract away from special casing just a bunch of different cases. Focusing on large inputs then also simplifies the analysis, because certain cases, certain boundary conditions don't play much of a role. We'll see examples for that. And sometimes you need to do this because one algorithm might be better for small things and then might go slower, and another one might be better for larger things. And generally, we think of the second algorithm as better. One way to think about this is, if I ask you, what's the fastest mode of transportation to get from point A to point B? It's really an unknowable question. If that is from here to the door, I'm probably faster than any mode of transportation that's just run, right? If you start laying down a train track, and in 5 years' time, or maybe, well, this is England, right? Maybe it will never be built, but let's not get political. So maybe you lay down this train track and you start your train, and it'll speed up and well, stop right away. That's not a fast way of traveling. But asymptotically, if the distance is from here to London, I don't want to walk. And if you have a train, that's probably a good way to go. It's probably the fastest way to go, right? So that's why we focus on large inputs, or in this case, large distances. If you want to know what's with the parts where it matters, because overall the cost will grow with the input size. So the big inputs are those that you need to get right. For those you want to focus on, and you want to find the methods that are effective for those. Mathematically speaking, asymptotics means we look at an approximation of a function around infinity. That's an informal way to state it. And here's an example that maybe illustrates the point. This is one long function. It has a parameter n, and it tells you, for example, I've made this one up, but maybe there is an algorithm that has that running time. And it's a very long term. It looks complicated, and it's not really clear how fast it grows. You have to look very closely before you see it. Here's a graph of the function. You see it has these weird jumps at powers of 2 and all that nonsense. But there's a much simpler, much smaller function, a smaller term for a function that captures the growth of that function very well and is much simpler to write down and to understand. And in this case, this will have a precise meaning, this little tilde symbol. That's the kind of asymptotics we like. They take away the complication from a function and leave the important bits, but are easier to interpret. OK. I'll jump right into the formal definition of what the standard asymptotic notations should be defined like. Now, caveat, not everyone defines them like this, but they're mistaken. I've been working with these for many years, and that's the definition that causes least trouble. Trust me. And we can debate it offline if you want. First notation is the tilde that you've just seen. And we say two functions are asymptotically equivalent, or f is tilde g, exactly when their limit converges to 1. If you take if their quotient converges to 1. So you divide one function by the other and take the limit for n to infinity. OK? The more widely used relatives with this big O is defined somewhat similar, but it's a bit vague, a bit looser. So we say f is big O of g. If you take f and you divide it by g, and that quotient is bounded. So there's some number so that this quotient stays below that number for any n. At least for any n up to starting from some point, but you can alleviate that. There's a second definition. If you can read that, then fine. Otherwise, ignore it. It's the same. Note that big O should really be a set of functions, but it has become customary to write an equal sign where it should really be an element sign. You just have to deal with it. What it really means, if you write something like this, is what's here on the right. The quotient is bounded. That's the formal definition anyways. There are two variants. There's big omega, which is the opposite. F is in omega of g if g is in O of f. And there's big theta, which combines the two. So f is in theta of g if it's both in O of g and in omega of g. These are the formal definitions, and they're most useful for checking in details. There's one more less known cousin of these, the little o. F is in little o of g if the quotient goes to 0. And the opposite is little omega. These are the formal definitions that are useful for checking. They're not intuitive, though. So let me also give you the more pictorial, intuitive notion, which 90% of the time gives you the right answer. But you have to be careful that there are some corner cases where it doesn't work. F is O of g is essentially the same as a version of f is less than g. And theta would be something like similar or equal. And omega would be greater equal. But f is less than g up to constant factors and for sufficiently large n. So if I take my function f, it might do some weird things for a while, but then there's a cutoff point from which on it behaves more stably. So that if I take my function g and multiply it by some constant number, it stays above the function f, right? That's what the definition says, and you can check how that matches the quotient limit and so on if you want. I'll come back to that example. For theta, it's basically combining two things. You can sandwich your function f between function g multiplied by a small constant and function g multiplied by a bigger constant. And again, before a certain threshold, the functions can do whatever, but after that, they stay in the right order. Okay? So morally, you should think whenever you read f is O of g, you want to read this is smaller. F is smaller than g. But with the caveat that it might be only up to constant factors and only for sufficiently large n. Okay? We could have a little fun with that example. Maybe let's skip this. You can look at the slides. Don't use plots like these for finite n to decide asymptotics. You can horribly be mistaken. And there's a nice example that I dug out years ago just to illustrate that point. Not so relevant for now. Let's see if that has sunk in. And let me go back to the picture. So or if you're hardcore, you want to see the definitions, right? Fun to watch the little bars go up and down. I know you can't see it, but right, in the interest of time, let's move on. Here's that. I'll comment on it a bit. Again, resist the urge to change your answer now. It's not really not gaining you anything. So answer B is what is essentially the right thing. If f is O of g, again, think of this as essentially meaning f is less or equal g. And that means g is bigger than f. Now, again, remember, what do the quotes mean? The quotes mean up to constant factors and only for sufficiently large n. Those two things you have to keep in mind. But because we're doing this on both sides, it works out like this. Now, there's something to be said for the last point, but that's a nitpick. If function f is identically 0, then you get trouble with the definitions by dividing by 0 and so on. But that's, we won't deal with so many algorithms that have cost 0 straight out for all inputs. So it's, mathematically speaking, this is only true if f is not exactly 0, the 0 function that is 0 at every point. Why did I present you the definition with the quotients? Because after all, that's, if you want to check asymptotics, the easiest way to do it. So let's have a few small examples on how you use this. So this first example, okay, has two statements. Let's pick this statement. This longer function is supposed to be in asymptotically equivalent to this smaller function. So we have a large function that's called f of n, and we have this one, let's call that g of n. So the first claim is that f of n is asymptotically equivalent to g of n. So if you look back to the definition, I'm not going to do it because I know it by heart, but you can go back. What you should check is that the limit of the two functions should converge to 1 when n goes to infinity. So how can we check that? The long form of this would be that. Now I'll insert f and g again. 20n cubed, 10 ln 10 ln n plus 5. That's a fraction with the sum in the numerator, so we split it. We have 20 over 20n cubed over 20n cubed. That's otherwise known as 1. And then we have these other two. N ln n over 20n cubed. Now for this last one is maybe obvious without thinking. We have a constant and divide by something that gets bigger and bigger and bigger. So that's 0. For that one, you may have to think a bit harder, so we can cancel a few things. Here it's also still easy. We can cancel 1n with 1n. And log n is less than n. So we can upper bound it by, so let me do this in small. We can say this is less than 10 divided 20n, because log n is less than n for large enough n. And so again, we have something that goes to 0. There's other ways to do it. If you have the quotient of two functions and both go to infinity, you can use L'Hopital's rule, which means take the derivative of the numerator divided by the derivative of the denominator, and then take the limit of that. If you keep doing that a few times for all polynomials and logarithms, that will resolve to the answer. Now, I also respect the comment at the bottom here. But this module is not an analysis class, so I'm fine if you use Wolfram Alpha to compute limits. I'm not really here to teach you limits. It would be useful if you were able to compute a few simple limits, just because I think it's common knowledge that is useful to know. But if you have to, use that. Now, we can use the same calculation to also do this second part.
Why it is theta over there, theta of n cube? Because of Scheider notation.
Well, I haven't explained that part. So so far we've only shown this part, the black claim. If we also want to prove this one, theta of n cubed. One direction. So first of all, this means two things. It means f is O of n of this one, and omega of this one. For the first part, we have to show that f divided n cubed stays bounded. And we've proven that it converges to 1. So it is asymptotically less than 1. Right, so we've shown that it converges to 1, and that means it is bounded. There's an upper limit you can put on the value of that thing, and that already implies the first statement. Now for the second statement, we have to invert the two roles. But luckily, we can use essentially the same statement. If that converges to 1, that converges to the reciprocal, and that's still 1. So it also means that this is bounded. And that implies the second claim. Let's do this example as well, at least part of it. So again, what do we have to do? We have to take the quotient of the two functions. And now you need to know the logarithm rules to work that one out. If there's an exponent inside the log, you can pull it out as a factor. And I have to divide that by log n. And now here I've done some nasty things. What does log mean without this LG? LG will always mean log with base 2 in our context. And inside the big O, it doesn't matter what the base is as long as it's any constant. Because all the logarithms differ just by a constant factor if the base is different, if the base is a constant. So we might as well put a 2 here as well. And then you can do the same trick. You can cancel the log on that one. And this one, log is less than log. So it converges to something less than 1. So in this case, it converges. The quotient is 6 if you pick log base 2 here. And so again, by showing that the quotient converges to a constant, you've shown that this divided this is upper bounded, and also the reciprocal, this divided by this, is bounded. And that way you've proven both ways for theta. So if we call this f again, and this g, and that's all we had to prove. The last example doesn't even need a computation. It's just pointing out some idiosyncrasies of these definitions. That's a humongous number, probably about the size of the universe in some measures. The number of protons in the universe is probably less than that. But it's still a constant, so it's O of 1, because if you divide 10 to the 100 divided by 1, that's still bounded by 10 to the 100. So again, if you have two functions and you want to check some statement like this, you take the quotient and compute the limit. You compute the limit either using tools like Wolfram Alpha or the analysis 1 knowledge you learned either in high school or at some university class. We don't really need any fancy limits. Most of the limits can be dealt with the simple rules that you have learned there. But it's not the main skill I want to check. I want you to apply the definition and conclude the right things. Good. Let's do one more wake-up call. Well, we're almost done for this unit. There's two little things I want to point out, two little other things, little features of these asymptotic notations. One is in this question. I'll wait till 80 people have voted. All right. So there you go. In past cohorts, it was almost equal, but this time you've done pretty well. But quite a few people also said no. So why is it true that this function is in theta of n squared? Well, there's actually nothing really weird to do. You do the same as we did before. You take the first function, you divide it by the function in the parentheses, and you study the limit of this. Right, so obviously we cancel the n squared. So what's left is not a constant fact, is not a number. It's still something that depends on n. That's why the definition doesn't say quotient converges to a number. It says stays bounded. Famously, sign is between -1 and 1, so it's at most 1, right? So this whole thing is at most 3. And okay, here it also becomes relevant for the first time. If you remember, the definition took the quotient and then the absolute value, just to make sure that in case things go negative, positive, we don't get into trouble. But that's all we need to show. So that means the von implication, sine n plus 2 n squared is big O of n squared. And for the other direction, we have to take the other quotient. So because in this case we don't have a straight limit, we have to do both, at least in your head. All right, so we again cancel. Maybe could have skipped. This time we again want to bound. It's a fraction and we want to upper bound the fraction. That means we have to lower bound the denominator. Sine is always at least -1. So if I put in -1 here, I get an upper bound. Let's do this slow. -1 plus 2. And that's 1. Okay. So also the reciprocal, the other quotient, taking that function divided by that one, is also upper bounded. But the function itself fluctuates, doesn't matter. Good. That was caveat number 1. This is basically just for you as a cheat sheet. There's a few rules. All of those are fairly obvious if you go back to the quotient. If you have some function and you multiply it by a constant, that's still within the same theta class, because you just make the fraction, the quotient, a constant bigger, but it's still bounded if it was bounded before. More interesting, if you take the sum of two functions, that's the same theta class as the maximum of the two. Again, you can bound the sum as 2 times the maximum, and so on. You will discuss in more detail in the tutorials examples on how different functions relate. These are kind of named classes of function growths that often occur in algorithms. So that's why I listed them here. Otherwise, there's nothing special about them. Now I want to finish with one concrete example from analyzing an actual algorithm and seeing how the asymptotic notations might help to express things in a clearer way. What you see on the right is an algorithm to compute some number to the mth power, where m is an integer. Now, of course, there's many ways to do this, and the algorithm is somewhat smart, but it doesn't matter so much what it does. But it computes this without doing all the m multiplications. It does this by repeated squaring. But to make it work with any number m, you have to do some trickery. Again, as I said, this is not really so important. This is actual Python code. That's one way to get a list of the binary digits of a number in Python. Ignore this kind of weird stuff. That's Python specifics. But you can do this. If you have a number, you get a list of the digits in the binary representation of the number. Then you start with 1, and then you iterate through all the bits. You always do a multiplication, and if the bit is 1, you do another multiplication. That's the algorithm. OK, fine. How fast is it? Let's count the number of multiplications. OK? So there's one multiplication happening in line 6 and one happening in line 8. I guess these line numbers have moved. So this should be line 6. This should be line 8. The overall cost, if we have these conventions for the input, so the number of bits in M is n. Then we have exactly n operations here, because that loop is run through n times. And then the other one, we don't know exactly how many times, but if we have the number of ones in the binary representation of n, then we know. That's just a bit unwieldy. But it's obvious from this that it's at least n and at most 2n. OK? Question. From what we've shown here, what can we say about this algorithm? I want to stress here that we're after the most precise statement that you can make. So there are many correct answers to what you can say about C, but I want you to be as precise as possible without lying. All right, I think you can see, right? I didn't show it, yeah. I mean, just because it has the biggest blob doesn't mean it's correct, right? And yes, I know Slider supports smileys and emojis. Oh, someone found out how to type the square root. Oh, you copied it from... No, I didn't put it here. Fair to say that we have different answers. The most precise one, yeah, I know, this is deteriorating now, so I'll let you have fun. But I'll move on. It's getting late, I know. So the most precise statement you can make is theta n, because you can both prove the upper and lower bound. So let's briefly go through why C of n. We have this function C of n. Now we divide it by n. We don't really know what C of n is. There's a plot which, oh my God, looks a bit crazy, right? It's not a nice function. But you can still upper bound this by the 2n that we've had. So that quotient is bounded by 2. Fine. And I take the other quotient, n divided C of n. Then again, I upper bound this time using the lower bound for C. It's very similar to the sine example we've seen before, except that here there's not even a hope of specifying what C looks like precisely in primitive terms. But as I can say, this is at most 1 because C is at least n. So I've proven both of the quotients are bounded. Hence, the function is in theta of n. And I can't make a more precise statement with the notions we've had. I can't easily say a tilde statement unless I have some some more concise way to express the function. And of course, you can express this in terms of m if you substitute that back in. So my last point from this is what's in the box down here. Usually, it's good enough to think of theta like tilde with a constant that you don't care about. Right? So f is roughly g up to constant factors and for large enough n. But sometimes there is no single constant that makes this true. It might be a case where the function weirdly fluctuates between an upper and a lower limit. And you can still make this theta statement. But there's no single constant that you could stick to n that would make it asymptotically equivalent to f or c.